Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael Sindinechi. Our topic today is Module 041, Electronic Measuring Instruments. This lecture is part of our series on Theory of Electronic Instrumentation and Measurement. Before we continue, please follow me in my lecture series by subscribing to my YouTube channel at https://youtube.com/@ndinechimichaelc. Please like, share, and drop your comments in the comment section or reach out to me using my email addresses. Also, listen to my lectures on Theory of Electronic Instrumentation and Measurement, and the other one on statistical analysis of errors in measurement using the links provided. We also have free lectures on Ebony Educational Consult website at www.ebonyeducationalconsult.com. Listening to these lectures I mentioned will help you understand this topic better. Electronic measuring instruments use amplifiers and other circuits to generate a current proportional to the quantity of variable being measured. Measuring instruments are very important when you talk of instrumentation and measurement. And the basic instrument for carrying out these measurements is called the voltmeters. There are different types of voltmeters, but no matter what the class is, it could be classified as analog or digital voltmeter. The digital voltmeter provides the opportunity of direct readout, which reduces human error due to parallax and increases reading speed. Digital voltmeters, as we'll see later, the advantages makes it easy for even unskilled person to use to take measurements and get the accurate result. So in this our lecture, we'll be concerning ourselves with the operations of the digital voltmeter, as the analog one is getting obsolete. Now, the digital electronic meter, which is usually abbreviated to DVM for the digital voltmeter and DMM for the digital multimeter, indicates the quantity which is being measured by a numerical display rather than by a pointer and scale used in analog instruments. The digital presentation can take the form of front panel readout or an electrical digital output signal. Digital voltmeters are distinguished from other voltage measuring instruments because of their speed, the automatic operation, and programmability. You can program them to feed another device. You can program them to give you output the way you want it. So several varieties of these digital voltmeters exist, and they differ in the following ways. One, number of measurement ranges. That is, if the voltage you're measuring or the variable you're measuring you anticipate that it is not going to be more than 10 volts, for instance, you can switch your measurement range to 0 to 10 range so that it will give you a wider reading, that is to higher number of decimal places. If you feel that it is going to be between 1, 0 and 20, you set your range between that 0 and 20. So this helps you to get a more accurate record. Take for instance, if you are measuring something that is just about 1 volt and you go and set the range to something to the range of 0 to 100 range, you see you may not be able to get the actual reading. So it helps you to narrow the range of which you want to do that. Then the number of digits. This has to do with the number of decimal places it can give. The more the decimal places, the more accurate your reading will be. And of course, accuracy, speed of reading, and it has normal mode noise rejection. When we talk of noise, you may have disturbances in your signal you're measuring. The DVM will be able to reject that noise. By noise here, we mean unwanted signal. Also, the greatest single distinction between types of these DVMs is the method used in converting the analog DC signal into a digital presentation. Remember, most of the real world thing you will be measuring will be in analog form. Now, this analog signal must have to be converted to its digital. Now, the methods involved or available for you to use in converting this analog signal into digital signal for use in DVMs are: one, non-integrating methods. Under these non-integrating methods, we have what we call the potentiometric method. Amongst the popular one under this potentiometric method is the successive approximation method. As we go on, we will look at this successive approximation method. Then we have also one called the ramp method. Under the integrating methods, we have the voltage to frequency converter, we have the potentiometric to integrating, and we have the dual slope method. Now, what are the advantages of this DVM? The advantages include that they are more accurate than the analog meters, and they have an accuracy of about 0.005%. You can see it is a very high accurate instrument for measuring your variable. So again, a definite number is provided for a particular reading so that any two observers will always see the same reading or value. If you recall, in our first lecture on instrumentation and measurement, we say that this is the human error called parallax, and it is very, very prominent in analog scales, analog meters, the big source of error. So the DVM eliminates that error completely, called the parallax error. The reading can also be fed to recorders or tapes where a permanent record of the reading is needed. In other words, you have, it's possible for you to record or store your readings for future use. Now, in dealing with this electronic digital meters, you must be able to convert the analog signal to digital signal. So we now have to talk about analog to digital converters. The digital voltmeter can be considered to be basically just an analog to digital converter, ADC, connected to a counter and a display as shown in Fig 1. If you look at Figure 1, just like having an analog input signal, analog to digital converter, then the output is fed to a counter, and as the analog signal is being converted, the counter takes, cognizance of the number of conversions and display it. This is a simple block diagram, but in each of the blocks, there are lots going on. So as we go on, we will see two examples of what is going on inside each of the blocks. So you say the voltage to be measured, which is an analog quantity, is sampled at some instant of time and converted by the analog to digital converter to a digital signal. That is a series of pulses with the number of the pulses being related to the size of the analog voltage. You can look up, how sampling is being done at some instant in time in my previous lectures where I treated sampling. That will give you idea of what is happening in the first block called the analog to digital converter. If you subscribe to my channel, you will be notified when we will look at the internal circuitry of what counter. Because the display could be, just any form of readout, any graphical user interface. Now, these pulses are counted by a counter and displayed as a series of digits. There are a number of ways the ADC can convert these analog signals. The commonest ADCs are the successive approximation method, the dual ramp, the flash ramp, the microprocessor ramp, and the voltage to frequency converter method. So in this our lecture, we will look at just two of them, the successive approximation method and the microprocessor control ramp. Successive approximation method, I would say, in this successive approximation method, a sample of the analog input voltage is taken, and compared with a voltage which is increased in increments until its total value reaches the input voltage. The diagram is shown in Fig 2. This incrementally increasing voltage is produced by a clock emitting a regular sequence of pulses which are counted and converted into an analog signal by a digital to analog converter. See the diagram. The resulting analog signal is compared with the input voltage, and when it rises to the level above it, the value from the clock is registered. The measurement cycle continues through a series of successive approximations until the signal reaches its final count. The measurement cycle stops, and the digital output of the counter represents the final approximation of the unknown voltage. Let's look at the diagram and see what is happening. Now, to the left, you see the input voltage, which enters into the sample and hold circuit. This sample and hold circuit is a series of now you see the comparator. The comparator is just an op amp connected without a feedback. So it has two inputs. I want you to, convince yourself by looking up how an operational amp acts as a comparator. One of the inputs is called inverting. The other input is called non-inverting. I want you to, look up your op-amp circuit and see two of these inputs where we have Vin and Vref. Which one is inverting and which one is non-inverting? That is an assignment for you. Now, in this successive approximation circuit we are looking at, you see the digital to analog converter. You see the clock, you see the counter, you see the digital output, you see a gate. When the signal is sampled, a sample of it is fed in to the comparator through the Vin. Now, as startup, when that Vin is, there is input there, and the Vref has no input. What happens is that the comparator looks at the reference, which at this point is 0, and the Vin, meaning something coming in, automatically the comparator gives an output because the comparator looks at the two inputs, and if Vin is more than the Vref, it gives an output. Because at this point, Vref is at 0 level, what is coming in Vin is automatically higher than 8. So it gives an output. Now, a clock signal comes also to the input of the gate. Now, this being an AND gate can only operate when the inputs are in one state. So the comparator brings an output, the clock gives an output, so the gate gives an output. That output is sent to the counter. Then from the counter, it gets back to, because what is coming out from the gate now is a digital signal. It's either 1 or 0, yes or no. So it is a two-state signal, making it a digital signal. Now it's fed into the counter. Depending on the number of bits you are using for your counter, in our diagram, it is 4. By using 4, it means that we can have maximum of 2 raised to power 4 combinations. So, which is 16, 0 to 15. So this is sent back to the digital to analog converter. When it is sent, then it forms the input to the next level of Vref. What is coming in again from the V in will be compared with that which is being fed to the Vref. If it is still higher, the same thing, the same process repeats. So it will continue until at the end of the sequence, what is contained in the counter is displayed at the digital output. That is the closest approximation of the input voltage that is coming into the system. That is how the successive approximation method of analog to digital converter works. So we can look at the next type, which is the microprocessor control ramp type digital voltmeter. This is a bit more complicated because it involves, use of microprocessors. At this point, I will still ask that if you subscribe, in our future lectures, we'll be showing how microprocessor control systems work, and we'll be able to take you through how you design your microprocessor-based device, so that maybe in your final year project, you should be able to pick a project that will enable you use microprocessor to make a design. It's very interesting. So I feel that if you subscribe, you'll be able to be notified when we are going to look at microprocessor systems. Now, the basic building block of the microprocessor control ramp type EVM is as shown in Fig 3. Here, input 1 of the multiplexer is grounded while input 2 is connected to the source to be measured, and input 3 is the reference voltage. Again, it has the comparator which accepts the output from the mux and the ramp voltage from the ramp generator. The microprocessor remains in its rest state until it receives a command to start conversion. Each time the ramp generator is reset, it produces a ramp. And what we mean by ramp is that it produces a sawtooth wave whose duration and amplitude remain constant. I guess that by this time in your studies, you must have met, sawtooth waveforms, sinusoidal waveforms, square waveforms, and other forms of waveforms. So anytime we refer to a waveform as a ramp, it means we are talking about sawtooth waveform. So when a conversion command arrives at the microprocessor, the multiplexers, which is abbreviated MUX, connects input 1 of the comparator to its input and brings it to the ground potential. Now, let's look at the diagram. If you look at this diagram, see that it contains more components than the successive approximation method. This makes this method also even more accurate. Remember, the first one we looked at, we said is an approximation. Even though that approximation is very close to perfection, this gives better result. So what happens here is, if you look at to the left, the block that is painted in purple, you see the input voltage you are to measure will come in at the rest state, the microprocessor is, attached to that input signal conditioner. So when we talk of signal conditioners, we talk of, things like filtering to make sure that there is no harmonics in any form, that it is exactly the signal we want that we are handling. So we call that signal conditioner. So it has its own circuitry. Then you have the reference voltage, like in the successive approximation method, we saw the reference voltage. So these two signals coming from signal conditioner and the reference voltage is fed into the multiplexer. And multiplexers concentrate so many inputs into one output. So you see, there are inputs to the multiplexers and one output. Now, the microprocessor receiving clock signal will also feed that clock signal to the ramp voltage generator. And the input to the comparator, we've seen what comparator does, compare the incoming voltage from the multiplexer and the ramp voltage output as the reference. So immediately the multiplexer is higher than the ramp, the comparator sends an output. That output is fed to the microprocessor and serves as the next input to the multiplexer, which also sends the signal to the input conditioner that conditions what is coming again as Vx back to the multiplexer. So these are combined together at the multiplexers to give a fine output which gets back to the comparator, and the system continues like that until the signal you want to measure is being taken. Remember, the speed. So immediately you connect the signal, in microseconds, the thing is taking place. So we say that the microprocessor remains at, 0 state until get command to start operating. So that command comes from the clock. Immediately it is clocked to start. It takes, the readings. So you can see that the comparator reading output, which is fed into the microprocessor, will quickly from the microprocessor be fed to the output. So that is the cycle anytime you want to measure your signal. Of course, when you are measuring, you have two terminals. You can see terminal 1 is grounded. So you ground one of the input terminals of your voltage you want to measure, while the other terminal gets to the signal conditioner. So with that, immediately the clock arrives, signal arrives, your measurement will take place. So that is how the microprocessor-based ramp DVM. This microprocessor-based has many advantages. One, its scale size remains constant due to zero drift correction. The signal conditioning makes it possible. The accuracy of the instrument is not affected by the time and temperature instabilities of the circuit element values, because you have, if you use lump circuits, you expect to have some instabilities. It is ruled out in the microprocessor-based RAM type BVM. There is a good repeatability in switching instance in the presence of noise and interference. This is because the RAM approaches the point at which the comparator operates always. However, there is a small disadvantage. Any noise that manages to cross the signal conditioner can no longer be suppressed. Point, say, join me in the next lecture on instrumentation and measurement, which will be on generation and analysis of waveforms. Like we have seen here, you have to have your signal generator, which you say in this case is a sawtooth, but there are so many other signals that is being used, and these signals are generated internally in the system. So we'll be looking at oscillators to see how this signal starts and generates on their own. So it is very important for us to know the conditions for oscillation to take place. And while doing that, we'll be looking at the RC, LC, and square wave oscillators. We also look at function generators and timers. While we are doing that, we now meet things like Schmidt triggers, and you know how they work, because in real life, the analog signal you are going to look at are not going to be perfect sine wave or cosine. There may be voice signals that doesn't have perfect, wave. So when you meet that such, you see that it becomes necessary for you to know how to handle that by knowing how Schmidt triggers work. So in our next lecture, we will be, looking at them. So I will, advise that you subscribe so that you get notification when we handle such lectures, which is a very important aspect of instrumentation and measurement. So, small assignment for you. You can put your answer in the comment section. If you get it right, I will let you know. If you didn't, I will help you answer them. So, in figures 1, 2, and 3, which you have seen in this lecture, what are the typical circuits that are referred to as signal conditioners? That is, if you open that box, we call signal conditioner. What are the typical circuits you will see inside? If you open the box we call the comparators, what and what are you likely to see inside the circuit? If you open the sample and hold box, what are the likely circuits you are going to see? If you open the multiplexers, what are the likely circuits you are going to see? You can do yourself some good by trying to use your hand to sketch some of these circuits instead of just mentioning their names. Thank you for listening. Please subscribe to the channel so that you get notifications.